We still have one balanced term left inside the bracket for the expression of gate delay. So we have already taken a look at the delay equation. We have already concluded that the first term P represents the intrinsic delay or the parasitic delay of the gate relative to the intrinsic delay of the inverter. However, when we start to look at the second term, it's going to be a lot more complicated. And the reason for that is that it includes C external, which is a delay, a capacitance or a load that is external to the gate we are looking at. So if we compare this bracket to this to a similar bracket we saw for the gate, for the inverter, it was Tp naught plus into 1 plus Fj over gamma. And so the second term here contained Fj, which is fan out, representing how much larger the second load is relative to the current load. So we should see something similar for gates. And in fact, when we take this term and start to expand it, we have R gate times C external over R inverter times CD inverter. Now we have two problems here, which is, first of all, we have C external, which is the gate capacitance of the upcoming gate. So it's C gate J plus 1. And at the bottom, we have a C drain for the inverter. So we generally want to compare gate capacitance to gate capacitance or drain capacitance to drain capacitance. But we know that there is a relationship between gate capacitance and drain capacitance, so we can replace C drain inverter with gamma C gate inverter. And this way we get rid of the difference or discrepancy between gate capacitance and drain capacitance. So that's taken care of. But the second problem we have here is that when we talk about fan out, we want to see the fan out of the next stage relative to the current stage. So we are at gate J, and the next stage is J plus 1. We want to see an expression of how much bigger gate J plus 1 is relative to the current gate J. And so when we want F to make an appearance in this equation, and therefore we want C gate for gate J to make an appearance. We don't have C gate for gate J, so we just shoehorn it in by multiplying and dividing by C gate J. When we do this, we end up with R gate times C gate J divided by R inverter times C gate inverter. And then we have C gate J plus 1 over C gate J gamma. Now, C gate J plus 1 over C gate J is something very familiar. We have already seen it with inverters, and we called it fan out. We can also call it fan out here, and we will. So we'll call it fan out, Fj, and this is Fj over gamma. Now, it's important to realize that fan out has a slightly different meaning when we deal with gates than when we deal with inverters, because when we deal with gates, we are dealing with different gates. And so how much bigger the next gate is relative to me is going to be not only dependent on how much bigger it is, but also on what kind of gate it is. So just keep that in mind, because with a chain of inverters or even a chain of similar gates, it's a little bit less complicated to think of fan out. But now we have a remainder term, which is R gate times C gate J divided by R inverter times C gate inverter. Now, this term is a unitless term, and it looks very familiar because it is actually very similar to P, which we just calculated in the previous video. But this term is different because it includes gate capacitances instead of drain capacitances. And so we give it a different symbol G, and we call it logical effort. And so logical effort is obviously a unitless quantity, and it's a ratio of time constants, and it measures basically how more difficult it would be for a gate to drive itself in terms of external current production relative to an inverter driving itself. So that's basically what's happening here. Now, how do we calculate the logical effort G? It's actually very similar to how we calculated P. We notice that G is equal to R gate times CG J divided by inverter C gate inverter. And it will become a ratio of just capacitances. So G is going to be equal to CGJ over CG inverter for any sizing scheme that allows us to have R gate equal R inverter. So again, we are free to choose the sizing that we use because it's going to give us the same result for G. If you choose to size for the gate very small, its resistance is going to be small, but its capacitance is also going to be small. Its resistance is going to be large, but its capacitance is going to be small, and the ratio is going to be the same. So G, or logical effort, is a property of the gate. It's not a property of its size. And in fact, size is only something that is only determined when we finally find the optimal sizing of the chain. So let's take an example, and let's just do this logic gate. And so this logic gate does the function A plus BC all bar. And what's happening here is that we're going to size this gate first so that it has resistance equal to the unit inverter. So 1, 2, 2, and all 4s in the pull-up network. And then we're going to calculate G as the ratio of input capacitance. And at this point, it's important to say that for logical effort, there can be multiple values for the same gate. Because logical effort is the effort to drive a certain input. It is not something, it is the effort to drive a specific input. It is not something that is only a function of the gate itself. So for example, for input A, we calculate the logical effort as the input capacitance we see, which is 1 plus 4 over the input capacitance of the unit inverter, which is 3. So this is going to be 5 over 3. But this is only for input A. Because if you look at either input B or input C, you're going to see an input capacitance of 2 plus 4 over 3, which is 6 over 3, which is 2. So you have two possible values of logical effort for this gate. In general, for a gate with n inputs, you're going to have n possible logical effort values depending on the architecture. Some of them might be equal, as was the case here with B and C. So when we use logical effort, we have to be careful which input is being activated in the chain we are looking at. As with P, there's nothing that says that we have to use a specific sizing for calculation of logical effort. But if you use any sizing other than that which gives you resistance equal to the unit inverter, you have to take resistance into consideration. And so even with this general sizing, we can still calculate G, but we have to use R gate times C gate times C gate and R inverter times C inverter. So the resistance of the gate is going to be R naught over K, and its input capacitance for input A is going to be 5 C naught K. And for the unit inverter, the input resistance is R naught and the capacitance is 3 C naught. Now the K's are going to cancel out, the C's are going to cancel out, the R's are going to cancel out, and we will end up with 5 over 3. So again, whatever sizing you use, you're going to end up with the same value of G. So you might as well use sizing that allows you to ignore the values of resistance and calculate G just as a ratio of capacitances. Now, when we look at the delay equation for the gate, TPJ, it's now Pj plus Gj times Fj over gamma. Now, G is logical effort for stage J. F is sometimes called electrical effort and sometimes called fanout for stage J. And P is the parasitic delay or intrinsic delay of stage J. When we look at the corresponding inverter delay equation, it's 1 plus Fj over gamma, which tells us that P and G for the inverter are both equal to 1. Like P, logical effort is greater than or equal to 1, and it is equal to 1 for and only for the inverter. So no gate can have a logical effort less than 1, and only the inverter can have a logical effort equal to 1.